Over the next several videos, we are going to be discussing the physics system found within Unity.
Probably one of the coolest things you can play with in Unity.
Oh, easily the most fun. You can do all kinds of fun stuff with this without even having to touch a line of code. You can just create up all kinds of cool simulations. It's like playing Mousetrap in 3D. And then being able to walk through it and actually watch it all happen. It's just a whole lot of fun. But it does require a bit of technical knowledge. And I want to throw out kind of a general warning that while all of this stuff that I'm going to be covering is relatively simple and it shouldn't be difficult for anybody to grasp, to understand, and start using right away, it is something you're going to have to pay close attention to, and I would highly recommend you take notes. Some of the descriptions that I've got to go through are relatively technical, and we've got to go through some objects, some components that have a lot of different properties. And it's going to be easy to get lost later on down the road. So I just want to kind of throw this out there that while this stuff is easy to understand, and I'll make it very easy for you to follow along with. That's not a problem. But it is pretty technical stuff. So please make sure you have your thinking caps on.
Right. It's not to the point where you need to have a calculator or your slide ruler out to figure this stuff out.
Though if you want to, that's really cool.
But there is a lot of different settings that we'll be going into, a lot of different properties that you'll have to understand how they interact with one another to actually accomplish the physics simulations that we're going to be doing.
Another thing that I'd like to kind of pitch out there is that while all of these different aspects of the physics system are very easy to understand and work with, mastering them to the point where they can be usable in a game will take a lot of practice. So be sure to play with them, have some fun with them, and really see how everything works and get used to them. Now, first off, there's just a few things I want to get kind of understood, sort of out of the way, and that is, this is sort of a point of interest more than it is anything else. Unity uses NVIDIA's PhysX. For its physics calculations. It's built right in. Now, if you are coming to Unity from, say, a 3D package, like 3ds Max uses Havoc Reactor. Maya generally uses Nucleus these days. They're all different systems, different engines that are used to calculate physics simulations. In this case, we're using NVIDIA's PhysX.
Right, so if you have a modern NVIDIA chipset, you're good to go because the drivers support PhysX built in. If you don't, you're going to be using software emulation to pull this off. So that's something you have to take into consideration when you're designing your games. Not everybody's going to have PhysX capable graphic cards, so you can't go crazy with the amount of calculations and objects you're throwing around inside your world.
That's right. Though, I mean, some of the more powerful, like AMD cards, whatever.
The Radeons?
Radeons, thank you. I couldn't think of the name. Those are still going to run very well. They're just not native the way an NVIDIA card would be.
Right.
Just want to kind of throw that out there. Now, the next thing is that while, in the same vein in which I would mention that a lot of this stuff is technical and you should be taking some notes, there are some terms that you are going to be hearing quite a lot while we work with this, and we need to get those defined and kind of out of the way early on. So what I'm going to do in this video, just kind of close things out, I want to go over some terminology that I really need you to understand moving forward, and then we'll take some general notes over physics simulations, and then we'll move on and start looking at specific things. So in terms of terminology, the first thing I want you to know about are rigid bodies. Now, Lee, in your own words, what's a rigid body?
A rigid body is a representation of a non-deforming object inside of the game world that reacts with physics. It reacts with forces and
collisions. Yeah, absolutely right. It is a non-deforming object, and I'll just jot this down. That responds to forces. We'll say comma, collisions, comma, and joints, and that's just being a little bit over precise. We'll talk about joints here in just a moment. Now, when I say non-deforming, because that's kind of an interesting word, it's like, why would you say that? Why don't you just say an object that responds to forces, collisions, and joints? Well, if you're trying to associate everything with objects that you see in the real world, let's take a soda can, like an empty soda can. I mean, that responds to forces in the world. You can drop it off your desk. You can throw it at your friend if you want to, bounce it off their head. But if you kick it really hard, it's going to dent.
Or if you stomp on it, it collapses.
That's right. You're going to change its shape. And a rigid body doesn't do that. By definition, it maintains its shape. It doesn't dent, it doesn't bend, it doesn't fold, it doesn't collapse. That makes it very easy for the computer to calculate how it handles collision, because it doesn't have to worry about updating the shape of this object in the event of a collision of a certain amount of force. That said, we do have the ability to create such objects, like rubbery objects or cloth-like objects.
Like a beach ball.
Like a beach ball. And we'll talk about things like that a little later in a separate video. But for now, our focus is going to be for a good long while just on rigid bodies which do not, in and of themselves, deform. Now, another term that I want you to be aware of is colliders. And we've already seen colliders up to this point.
And we said rigid bodies, respond to collisions. We need colliders for rigid bodies to detect when they've collided with something else.
That's absolutely right. If you don't have a collider, then you have no way to calculate when that collision takes place. And again, we've already seen these. These are an invisible surface used to calculate collision. Now, the interesting thing is that they are invisible and they are entirely separate from the visible geometry that you see. So if you have a model of, I don't know, a chair, just a little wooden chair sitting somewhere in your level, and you want that to respond to physics, you're going to need to set up some sort of a collision surface for it. So if somebody was to knock it over, how would it land? Would the backrest of it actually hit the ground and bounce? Would there be some sort of collision with the seat? Of course, you want all of the physical aspects, all the parts of the chair should look like they're bouncing off the environment.
But you don't want to have a collision surface for every polygon that is inside of that model. You don't want to have a different collision surface for the legs and the spindles and the seat of the chair. You want to simplify it as much as you can to get the performance out of the checks.
That's right. And we'll talk a lot about colliders and how you can create your own custom colliders. We'll talk about using the primitive colliders that are already included with Unity. A lot of discussion about that, but the idea is just to understand that colliders are invisible surfaces used to calculate collision. Now, with just those two things out of the way, I do want to mention that in these cases, rigid bodies and colliders are also, they just happen to be components that are going to be added to your game objects. There is a rigid body component that you will add to an object that you want to become a rigid body, and there's also a collider component, which we've already seen, that will allow you to calculate some form of collision. Now, up to this point, if you've been watching any of our other videos, I mean, it's possible that depending on the order in which you're watching these, you haven't seen anything about colliders at all. But in an earlier video where we were setting up our level, we did see that we could set up colliders on our trees so that our character controller couldn't pass through them. And it's all part of the same thing. Now, moving on from here, we have physic materials. And notice my writing is slanting upward slightly. Wonder if I can stop that. Probably not. So you have physic materials.
Right. Now, these are slightly different than the typical materials you may be thinking of. They are materials in the fact that an object has a material. But where a normal material that you may be thinking of controls the way that material looks, how it responds to light, these materials control how that object reacts in a collision.
That's right. A physic material literally is a definition of physical properties that are stored in a modular asset.
So just like a regular material where we take a texture, we assign it to a material, and we take that material and drag and drop it on top of an object to control how it looks, we can create a physic material, add or define the properties of how we want it to react in a collision, and we can drag that onto a collider, and that will tell the collider how to act when it gets hit or it runs into something.
That's right. And we're going to be talking about these a lot more in their very own video. But just as a quick overview, you can think of a physics material the way you think of materials in the real world, completely apart from the computer world. And what kind of materials can you think of? Things like wood, concrete, glass, rubber. You could just go on and on. Various forms of metal. How do those objects respond in the physical world? And what kind of friction do they have? How do they bounce when they come into contact with other types of material or with themselves? What happens when you have that kind of physical contact? All of that can be defined inside of a physics material, and that physics material can be applied to multiple objects. The upshot to that is, of course, that if you have like 150 different metal boxes, I guess, in your game, and you're playing your game and you think, you know what, those boxes are just bouncing way too much. It just looks crazy. I need to tone down all of that bounciness. You don't want to have to go to each individual box and say, all right, take the bounciness, pull it down. Now select the next one, take the bounciness, pull it down. Which is why we have a physics material. You apply it to all of your metal boxes, then go back to that physics material, change one bounciness value, and it just propagates to everybody. And in that regard, that's how they're very much similar to an existing material. Because if you go back and change one material for an object a material that's applied to multiple objects in your scene, all of those objects will reflect that change in your material as well. All right, moving on down our list. Next term I want you to be aware of, and I'm probably going to need a new sheet at some point, is joints. Now, if you are a Maya person, this is the same as dynamic constraints. I just thought I'd throw that out there because I am a Maya person, so whenever I can, I like to make those associations. What a joint is a mechanism to constrain the behavior of a rigid body along some axis. So it constrains behavior along some axis.
Right. You use these to create effects like a door if you want it to swing on a hinge. Or if you're recreating the pit and the pendulum and you want a giant blade swinging back and forth, you would use a joint to accomplish that.
Exactly. And I think the classic example, however you want to handle it, is going to be a door. Whether it's like a doggy door that swings from the top or just a regular door like you have here, that, like the one I'm staring at our office right now, that just kind of swings inward. The idea is that your door would just be a piece of geometry, a box, with or without a doorknob, it doesn't really matter. And you would use a joint on one edge of it to control the hinge-like behavior of having that door swing inward when the player approaches it or hits it with something. Now, with joints out of the way, there's some other things. Now, these terms are really in no particular order. I kind of feel like I should throw that out there. The next one of these are forces. Now, a force is really just a... you want to say like a force is a force.
It's energy applied in a direction.
Exactly. It's an amount of energy that is applied to an object in some way. Now, you're going to use this primarily in the form of either joints, which has some force settings within them, if you want to control like a motor and make something constantly turn, or with a constant force component, which is a component you can put on a rigid body to constantly keep applying a force to it over and over again, kind of like an engine, to keep pushing it along in a given direction. So this is, you can think of forces as energy imparted to dynamic objects. And this really comes in two flavors. You have linear and you have angular. Angular force is also known as torque. And you're going to see the term torque pop up a lot. And all that is an amount of force that is being applied specifically to rotation. Where a baseball will go sailing depending on how hard you hit it with a baseball bat, a tire will turn more quickly based on how much force you apply to it. And that force you apply to it is torque. Now, I've pretty much filled up my sheet here, so let me just go ahead and get another layer out here. And we'll hide my existing layer, because we still have a couple more terms that I'd like to address. And the first one of these is, well, the next one, I guess you could say, is cloth. I'm bringing this out really because it's kind of a special case. I'll even put that in parentheses.
Right. With cloth, we had mentioned that rigid bodies do not deform.
Mm-hmm.
Cloth does deform. Now, the neat thing with cloth is that you can make it work in conjunction with a rigid body, and you can make an object react like a beach ball, where it actually does deform when it hits the ground or something hits it. It's a special case, which is why we're denoting it as a special case. But we can do some neat things with cloth. There are two types of cloth currently in Unity. One it being interactive, and the other being a skinned cloth. Now, the ones that we're going to play with here are the interactive cloths and not so much the skinned cloth. The interactive cloth is the one that we can use to create things like a flag, a tablecloth.
Mm-hmm.
We can use it to build things like trampolines. Lots and lots of examples you can do with interactive
Sure.
cloth. They react with physics. They look at other colliders and they deform their shape based on the colliders that they hit. Now, skin cloth is a little bit more advanced, and it requires a skinned mesh
Mm-hmm.
to interact with. It's actually they're faster than interactive cloths because there's less calculations involved, but they also require us to have a skinned character in our
Right.
scene,
And this would be like if you had a character that maybe had some floppy piece of clothing on them.
like a cloak or a
Yeah. Or even it could be even something simple, like you just have like a collar or something that needs to kind of flap around when the character moves, or you could probably get really clever and use it for hair and whatnot if you just really, really wanted to. But what this is going to do is take a skinned model and make some part of it, some collection of vertices on it, behave as if it was cloth-like. Blow in wind and flap around based on motion, that sort of thing. Now, that's all we're going to talk about in terms of that here. We're actually going to have some specific videos over cloth, but I just wanted to kind of throw that out there as a term because it is something that Unity can do. Now, finally, as we kind of wrap up this really quick, I guess you could say kind of like a physics primer for getting into Unity, there are some notes that I think are just noteworthy, notes that are very noteworthy. And the first one of these is that physics simulations control your performance, or they can have a serious effect on performance.
these can be very calculation heavy, especially when you start getting into mesh colliders, things that have lots of vertices. If you have hundreds of objects in your scene all reacting to physics simulation,
Mm-hmm.
you're going to bog down your system fairly quickly.
I'm just going to jot this down. You can remember this forever if you want to. This is the ever-present trade-off of game development.
And if you really want to kill your system in a hurry, put a whole lot of cloth in your game.
How good versus how fast. You're always going to be struggling against that, and physics is absolutely no exception. You can create the best-looking simulation ever. I mean, just something that is just eye-splinteringly amazing. You know, you crumble, you throw a catapult rock through the air, and it's got particles and smoke trailing off it, and it hits a brick wall, which shatters and crumbles a castle tower behind it and causes these ragdolls to fall off the castle wall, and it just makes you cry. It's so beautiful.
I want to make that game.
Yeah, but then you try to actually run it on a decent gaming system, and you're getting like one frame every 2 or 3 minutes. And that's no good. So you're always going to be struggling with that. By all means, play with this kind of stuff, but do a lot of testing as well to make sure that you're not going overboard with your physics simulations. Next note. Scale is absolutely critical to keep in mind.
Right. This system is based off of true physics calculations, meaning force and friction, density, mass, all of those things that you may or may not remember from high school physics or college physics apply here. So we are simulating the real world. So the physics engine expects things to be scaled as they would in the real world.
That's right. Remember that in Unity, 1 unit equals 1 meter, and that your typical character is somewhere around 2 meters tall. If you start messing this up, well, the reason this is so important, if you think about it, is take like a broom and knock it over and see how long it takes to hit the ground. And then, maybe get like a 10-foot board and knock that over and see how long it takes that to lay down flat on the ground. And then maybe knock over, I don't suggest you do this, because it's illegal in some places. But if you had like a big, tall, like redwood tree, just something ridiculously oversized, and you were to somehow chop that down, I don't even know how you do that, but if somehow you did, it would take forever, just such a long time for a really tall object like a redwood tree to fall all the way down to the ground. And they're doing the exact same behavior. They're all just tipping over and laying flat. It's just that because of the scale, it's going to take a lot longer. The simulation's going to be different.
Right. So if for some reason you may be building your level and all your assets and some external tool that likes to work in centimeters instead of meters, and you bring those into Unity and
You're not talking about Maya again, are
No,
you?
no, not at all. But if you brought in all your assets and you go, well, everything's in centimeters, so I'm just going to scale everything down by a factor of 100, your simulations aren't going to run the way you expect them to.
That's true. That's true. Now, there's one more thing I want to throw out as a note, and it's just kind of a reminder, because in an earlier video over the UI, we did discuss this, but maybe you haven't seen it yet for some reason. But that is to remember the physics manager. And while we spent pretty much our entire video here in the little whiteboarding section, I'm going to jump into Unity for just a moment. And here I've got a simple level already open, but I'm going to go under Edit and jump down to Project Settings, and we can jump over to Physics. And this brings up the Physics Manager here over inside the inspector, and you see what kind of controls we have. We can set up gravity, which by default is set to negative 9.81 meters per second. We have default material. This is our physics material that will be applied to any objects for which we don't specifically designate a physics material. It's like your fallback. It can be very useful. If you have like a sci-fi game where pretty much everything around you is metal in some sort, you could make one generic metal physics material and just use that as your fallback for anything that you don't want to manually define. You have a bounce threshold. This is going to control the velocity at which bounces will occur. So if you have an object that is moving slower than this value, you're not going to get a bounce anymore. You have a sleep velocity. This will cause your objects to stop being calculated if they slow down to below this value.
Right. They will go to sleep, and they will not be calculated in the physics simulation until the point they get collided with another product.
Or some force affects them, something to start propelling them through the level again. And the reason that this becomes useful is you might have a situation where an object is moving just a tiny little amount, almost imperceptibly slowly, like you really couldn't even watch it move. But that requires calculation, which is, whether you see it or feel it or not, that is slowing down your machine. That's one more process that has to be calculated. So by adjusting this sleep velocity, we can say if an object moves slower than this, just make it stop and let's stop calculating it. Same thing for angular velocity as well. How quickly can something be turning? Or I guess, more precisely, how slowly can it possibly go before we just finally say, all right, we're going to stop calculating that, just go ahead and stop it, put it to sleep right now. We have a max angular velocity. This is the maximum rate something can spin. A lot more useful than you might think.
Yeah, this prevents things from spinning wildly out of control.
Right, wild velocities. Because you can spin something so quickly, and I've done it in Max, I've done it in Maya so many times, I've even done it in Unity just by playing with settings, and I don't recommend it because you can really blow things up and you can crash programs. You can spin something so much, and if you get the timing just right with your processor speed, it'll look like it's barely moving at all. Like it's just really slowly spinning. It's the same kind of effect you see when you take like a camcorder, like the old style camcorder, and watch like a tire spin, where at some point it almost looks like it's not moving. Same thing, but some object rolls up to it and tries to get close, and it gets smacked and sent like halfway to Pluto because we were spinning so crazy out of control. Now, we also have min penetration for penalty. This causes me to jump back over to the whiteboard. Min penetration for penalty, I'm just going to pick on this little kind of blank area up here. Let's say I have an object. Now this object would be a rigid body. How do I know if another object has collided with this rigid body? I need to have a set distance to check and see if I have penetrated into it, because interpenetrations, if I have an object like here, and then I have another object like this is bad. You don't want this to happen. And so what we can do is we can check and see at what point that has taken place, and that's by setting up the min penetration for penalty. And so with a setting of, what was that set to, like
0.1?
0.1, we can go 0.1 units into the surface before we detect and actually throw back an error and say that we've got interpenetration problems and we've got to deal with that. Now, moving back over into Unity land. We have our solver iteration count. This is the number of calculations that the physics solver is allowed to calculate on each frame. You can lower this down if you need more performance, or raise it up if you need more precision. And again, this kind of comes back to, once again, that age-old question of how good should something be versus how fast should it be. Generally, I find that the default value of 6 works in nearly every case I've ever needed to. Raycast hit triggers. This is if you have any colliders that are set up to be triggers.
Right. This gets into the scripting aspect of it. What happens is a collider has a checkbox that allows you to turn it into a trigger. Once you turn a collider into a trigger, it doesn't calculate collisions like it normally would, but it does send an event to scripts that are listening for it to let you know that a collision has happened. What this checkbox does is tell that trigger to fire off the event in case a ray hits it.
Mm-hmm. And the last thing we have is our layer collision matrix. This allows you to choose what layers are able to collide with objects in other layers. So if you have an object that's in the default layer, it can right now it could collide with anybody. But let's say you wanted objects in the default layer not to be able to collide with water. Simply uncheck that. Now objects in the default layer can't collide with water. Or maybe you want objects in the water layer not to be able to collide with objects in the campsite layer. Then you could just uncheck that. So you've got that kind of power to control who can collide with whom. So that's a rundown of the physics manager. I know it's kind of jumping around a lot, but it's something that is important, and I do want you to know it's there. It is actually discussed in a separate video, but if you didn't see that and you don't want to have to do a bunch of looking around, I at least wanted to point it out and give you a really basic rundown of what it's there for. As a quick refresher before we close this video off, so we took a look at some basic terminology, starting with rigid bodies, colliders, physics materials, joints, forces, and you're going to be seeing a lot of these as we move forward. And then finally getting into cloth and how that works inside of Unity, and then just some general notes about how physics can really be a hit to performance if you're not careful, the importance of scale, and then always remember that you can tweak several different aspects of your physics simulations inside the physics manager. With that, though, we've carried on for almost half an hour, and I think it's time for us to jump in and actually start playing with the physics system inside of Unity.
It's time to have some fun.
That's right. So that'll wrap things up for this video. Thanks for watching.